recording is enabled. Now that, like, what we want to see the screen, like the last activity, what we were doing in the last class. Right. Actually, I changed the names of the files and all that, so that the program that we have written in the last class is the following. This is the program. And in this case, let me also enable this. So this is the actual program. What are we doing? We are the 8th line meant for creating a pipe, so that you are going to get two file descriptor numbers, which will be stored into P of 0 and P of 1. That's the 8th line, what you call declaration. And then you are also declaring other variables and all that. And this is the actual message that we want to communicate between the parent and the child process, right? And you are actually creating a pipe by using a pipe system call, by using pipe, and then you are passing on the array P, so that whenever pipe system call is successful, it initializes P of 0 with the input end of the pipe file descriptor, and P of 1 is initialized with the output end of the pipe. So that is the file descriptor there, right? And you are also displaying the file descriptor number just for our understanding. Every time, most of the time, you are likely to get 3 and 4, because whenever you create any file, you open a file kind of thing, you get the next available smallest free file descriptor number. Because every time you run a program or a process, you are going to start a process with 3 file descriptors. All of you are familiar with that. The 0, 1, and 2. Standard input, standard output, and standard error. So, and then you are actually now creating a new process. You are creating a process by using the system call called for. And we have already talked about that the file descriptors that are available with the parent process will be what? Will be shared with the child process. So essentially, all the file descriptors, whatever the files that you have opened in the parent process, they are also available in the child process. That is what we are actually trying to make use of, so that the pipe is now available in both the parent as well as the child. And you are going to use the writing end of the pipe in the parent process and write some message. And we are going to use the reading end of the pipe in the child process and do some processing there and all that. So that's the idea there. And then switch off CPID. So essentially, this is the simple pattern that we are using. Whenever you are actually creating child process and all that, so switch off the child process ID variable. And we know that the value of the CPID, the child process ID, or the return value of the 4 is different in child process and is different in the parent process. So its value is 0 in the child process, case 0. In this case, what to do? -1, it is a failure case. Most of the time, you may not actually see this. Very rarely, if already you have created too many processes, and if it cannot create one more, then this is the scenario. Default is the parent process, whatever is there. So what we have done, you are actually closing the in the what it is in the child process. You are trying to read from the pipe, so you don't require the writing end. So you are actually closing the writing end of the pipe, close of P of 1, right? And then you are trying to create a duplicate of your reading end of the pipe to be available also at 0. So your reading end of the pipe is also available on the file descriptor 0. Why are we doing this? Because whenever you load another program into the memory, and most of these things are filter commands. What are the filter commands? They actually read the data from standard input, do something, and generate the output onto standard output. So you are, without actually modifying any of these programs, you are able to communicate with those programs because you are making like the data available on the standard input, right? So how are you doing that? You have created a pipe, and then the reading end of the pipe is also made available on the standard input of your process. So do 2 of P of 0 comma 0. P of 0 is also available on 0. And grep will actually read from 0. Is equivalent to reading from reading end of the pipe. And then anyhow you are saying exec LP of. So this is a loader actually. You are trying to load a new program into the child process, into the child memory area. Until now, until the exec is executed, it is still running the same code as that of the parent process. And you can change the code to be executed in any process by loading a new program, by using exec related system calls. So you are saying exec LP of grep, comma. So this is the actual command to be executed, and you are using the path environment variable. That's why you don't have to give the full path. Just only the command name is good enough because it uses the path environment variable, searches in all those folders, and wherever it is available, it's going to load that particular graph. And these are the command line arguments for that particular thing. So first command line argument, 0th one will always be, in general, be the same command as that of this thing. And after that, the other parameters, arguments, whatever, 2. And ultimately, the list must be ended with null character to know that that is the end of the parameters kind of thing. Okay, so you are going. This is what we are still discussing the same program what we discussed in the last class, and we failed there. So we are trying to find out what is the reason behind the failure and give the solution also. And then the break anyhow. -1 break is understandable. And then default is like a close P of 0. This is the parent process. Parent process is not reading anything from the pipe. It is only writing onto the pipe. So it doesn't require the reading end. So close P of 0. And then write of P of 1. You are writing to the writing end of the pipe. Write of P of 1 comma message. What is the message? Whatever is the message that we have put here. And then how many characters are to be written? You are saying strlen of message plus 1 somehow. So this is what we have actually written the last class. So this entire thing ultimately strlen of message means only from only the characters that are involved in the message. If you say +1, it also includes then the null character also. So we are actually writing not only the message, but you are also writing the null character also onto the pipe. Remember that. And after that, you are closing the pipe so that the child knows that. So that is the end of the data kind of thing. So this is the program what we tested in the last class. The name of this file is pipe IPC grep fail. This is what we have given. Let us now see what is going to happen. Right. So let's compile also so that you understand. So what is going on there and all that. Grep, not grep, GCC, right? So for me, the problem input problem is there, GCC, and then followed by what? Followed by pipe. Pipe, followed by IPC, and then one more this thing. So it's not allowing.
Two dots.
Huh?
-2.c.
Not 2.
IPC.
It is grep fail. It's now the changed version. Like, yes, last class we have talked about IPC-2 only. But because I made some changes to that, I don't want to show that. Right? I will show you that later. But the same 2.c is now available in this particular file. So maybe you have written 2.c, continue with the same, no problem. Right. So whereas here, that particular thing is available in this here, -o, and then pipe followed by IPC, and then followed by hyphen, followed by grep fail and all that. So this is the thing. So anyhow, it is compiling. Compiling, no issue, even last class also. Now when you try to run this, when you try to run this, by using in this particular manner, this is a message that we got last class also. Binary file, standard input matches, something like this. So we are already at the end of the class and we did not want to waste time there and all that. So this is what we are getting. There is no problem with the program because we already tested with other related commands, not only grep, other things, cat or maybe NL or any other commands, any other filter command. You can always test with that particular thing. Even sort also we tried. Everything is okay. Grep here, it's not the problem with our this thing, but grep behaves, right, differently for text files and differently for binary files. So what is happening here is that if you examine our program, we have written not only the message, but even the null character also we have written. Whenever null character is seen by the grep asset, it understands that as if it is not a normal text file. It understands as if it is a like some raw data, like some what you call binary data. Null character means it like you can type even by using your keyboard. It's not available on any of the keys. So if you just simply say strlen of message only, so that means you are only writing only the message part. That means without the null character. Null character, why do you require? Within the main memory, whenever, like when you are going through the data one after another, to know that this is the end of the string, you are doing that. But in the file and all that, you don't require. Already there is an end of file concept there and all that. So null character is not required. But somehow we have written that. And grep is designed such that whenever it sees a null character, that means characters that you don't see normally on the keyboard kind of thing, it understands as if it is a binary data. Then it behaves differently for binary data and differently for text data. Right? Now what we have done, we have actually now removed that null character by removing that +1. So it is now writing only the message part of it, not the null character. Now let us see what is going to happen. Right? I'm just saving it. And again you are compiling. Again you compile this. Only one part, like that's the only thing that what we have made. Now you see, you can see the output is line number 2. Right? It is giving the answer. The reason is, like as you can see, what is that you are looking for? You are looking for 2. Grep for 2. You are searching for 2 in the data that grep is actually reading. Grep is getting that line 1, line 2, line 3, and so on. So that's the reason why line 2 only you are getting. But in case you say that like a line is what you say, you are trying to grep for line, for example, right? So here, what is the data? Hello, line 1 and all that, line 2, line 3. So in case you look for line, then you get all the lines, right? You need to get all the lines there, naturally. So I'm just saving it and again recompile. And again you run that, naturally you get all the lines. Hello, line 1, line 2, line 3. The dollar before hello line is the like prompt being displayed by the shell because there are 2 processes that are running. One is the parent process, because parent process is terminating very quickly. That's why once the parent is done, you are getting that dollar prompt. And then the output of both parent and the child is coming onto the same screen, right? So this is a troubling factor. The null character is a troubling factor. But even if there is a null character, is there any way by which you can instruct the what it is the grep command? It's a problem with the grep, not with the program asset. But even if there is any like null character, that kind of thing, still you want your program to work, let us say, right? So in which case you are again compiling here. So when you run this, you are getting this particular message. But grep actually has got another feature in the sense that, so if you pass on an option here, an option like minus a, right? Minus a means ASCII kind of thing. It is a normal text. So minus a followed by this, comma, like this. So grep has got an option called minus a, by which you know that like the data that you are actually supplying is going to contain some text. It may contain some other data also, raw data or binary data and all. Even if there is a binary data, still I want the output to be displayed. So you are instructing the grep that I am fully aware that this data may contain null characters or other binary data. Still you perform, you give me the matching lines. That's the idea behind. So grep minus a. When you do this, see here, still you are writing plus one. Still null character is being written. The only change that we are doing is null character is still returned, but grep, the way that you are calling grep is changed by using minus a now. So now I'm just saving it. You come back to compile this particular thing and then run this. Now if you see, you are getting still the same output. Essentially, that's the actual trouble factor. Just to know all these things, you can as well, like for example, going to the other this thing here, you are now analyzing the grep into the details, right? So for example, you say grep for like some student like David or something like that in a file called student. The other day we have written, right? So you are getting this particular thing grep David students, because students.txt file, it's basically a text file what you have there as a part of it. Now let us actually add what it is. Let us add to this some null characters to this particular file. How are you going to add null characters to the file? Either by editing, by using vi and all that, but you don't have any key there to type null character and all that. But for that you have something called printf statement, right? So there is something called printf. Printf. This command is there, and within this particular thing, when you say reverse slash 0, right? So it's actually going to it's writing that particular thing. How do you know what it is actually writing there and all that? Especially when you are actually seeing some raw data, binary data kind of thing, we use a command called OD, octal dump. So you pipe it now. What is going to write? So you can see here, it's actually there is a single character, and the output of that happens to be null character, 0, all 0. If you want to, you can also display if you want, you can also display here like both the character version of it as well as the other minus c. When you do this, see null character reverse slash 0, like it is displayed. So now what is our idea now? You want to attach this to the particular file, the text file kind of thing. How are you going to do that? Just simply append to students.txt. Now that students.txt has got this null character at the end of the file. At the end of the file. Now, because we have not modified anything, you can now, like for example, display that by using the cat command or whatever, cat followed by students. So what do we have here as a part of this? So we have all this. If you see there, in fact, the null character is not even visible there. It's only displayed. It has actually probably written that and all. So everything is there. Now you try to actually grep or search for something, right? This is what we want to. You see here. So what is that it is saying? Binary file students.txt matches. It's only saying it matches something like that. But like in case you give something that's not there, then it doesn't say anything. But in case it is there, it doesn't display actually. It doesn't display the matched outcome. Because there is a likely raw data or binary data which cannot be printed there or which may mess up your screen and all that. So it is only saying that it is matching, but it is a binary file. So even if it is a binary file, you want to see the outcome, then they have given you like an option is given to you. Like how do you do that? By giving minus a. So minus a followed by like this. When you give like this, now you are going to get the corresponding. So that's all. Like as far as your program is concerned, inter-process communication, the program what we have written the last class is absolutely okay. So only we are now analyzing the graph behavior with respect to the binary data and also with respect to the normal text. I hope everything is clear now. And not only that, like I have made like what it is simplified. We try to develop this IPC program as simple as possible. But in the process, we got some errors and all that, and again made the program to be bulky. But actual failure is not because of anything, but because of the grep related stuff. But let us now look into the simplest possible program using the IPC kind of it. Now all of you are familiar what's going on there and what needs to be done and all that. So this is the other thing anyhow. So no issue. So but in this case, as you can see, pipe IPC2.c, you are actually now trying to close, remove that closing part also, only duplicate and the remaining thing and all that. Let me show you the best possible, simplest possible program actually, right? So you don't require actually most of the other things, but for like what it is, because you are not using, you are trying to close them and all that, but you don't require to close any of them. This is the simplest possible IPC program, right? So what are you doing? You are actually create like this is pipe is like this P of 2. This is an array for getting the file descriptors. You require that, and then message anyhow you require, and then you are creating the pipe. You are not worried about what its outcome is and all that. You are always like optimistic, hoping that pipe will always be successful. But you can always get to know what is the return value of that, right? And then if it is an error, do all that and so on. But in case if everything goes smoothly, you don't require the return value of the pipe. So it is creating the file descriptor. After that, what do you do? After that, now you have to actually create a process. How do you create a process? By using the for. So straight away here, see, straight away here, you are saying switch off for, because you are not even interested in the return value of the for. Right? Anyhow, that's going to be used within the switch. So you are not capturing even return value of the for, but it is actually used within the switch. You are not using another variable for that and all that. So when you say switch of for returns two different values. So in the, as you can see now, so whenever it is case 0, so that means this is meant for what? This is meant for like case 0 means now it is basically the child process. Child process, what is to be done? Make a duplicate of reading end of the pipe to be available on the standard input. So this is what you require. This is important. You are making the reading end of the pipe to be available on the standard input. That's all, straight away. You are not closing nothing, that, this, and so on as such. Let like both the ends be there. You are not going to anyhow using writing end of the pipe on the child process. So you are not even closing that. Simply exec. Simply exec this particular thing. You can do any other command also. And then at the parent program, what do? Simply straight away write the message. Write to the writing end of the pipe. And then break. So the moment this program is terminated, automatically the pipe will be closed. So the moment pipe is closed, GLEP understands that all that particular thing. And here if you see that +1 you have removed, meaning that null character is not being written. So no issue. So this is the simplest possible program. So now what we do, we try to compile this pipe IPC simple.c, right? So let us now go into this particular thing. Right. So here, pipe IPC simple.c. simple here. Right. So GCC pipe IPC simple dot C minus O pipe IPC simple. So you are compiling this. And then run this particular thing by just simply saying, or instead it's better to use this rather than doing all that. See? So line number two. Line number two is the matching line, right? So you can give anything for that matter. Instead of two now, you are interested in, let us say, hello. So, or LLO kind of it. So this is what you are actually interested to display that particular thing. So now compile this. So run this particular thing. So you are getting hello line 1 is the only output that you are actually getting. So you can test with other commands as well and all that. So this is the simplest possible this thing because of our understanding and all that. And anything on top of it, you can always, because you are not using the writing end of it, you can close it, nothing wrong. But even if you don't close it, so it's okay. Like, because in case by any chance you try to write here, then this should be available on the reading end of the other side as well. So probably that is also, you can try it out, whether it's possible for the child also to write and then parent to read from that particular thing. You see, always all these things, so you can learn the things only when you experiment, right? But to experiment also, it requires some foundation, some grounding, where you are quite sure on certain aspects. And only on the new ideas, yes, you are experimenting. Only there you can make that change, this change, and try to understand what's going on, and so on, like that, right? So I hope everything is fine as far as inter-process communication is concerned. So as far as pipe system call, and then for, and then do, and then exec. Exec, you have other versions as well. So go through that Stone's textbook that is shared with you, the PDF file. So a lot of other details are also there for you to learn, right? So let's now move on to other topics. Essentially, the things that are left out now is something called locking, file locking, and then signals. These are two important concepts still to be covered as far as the first mid is concerned. We don't know still yet, like no announcement is made whether the mid exam will be conducted next week. Like most likely it may not be there because of the still lockdown continuity and all that. So you will get appropriate notifications. So follow that, and accordingly it will be there. So in case there is no mid exam, like the classes will continue, and the second mid concepts are going to be covered, and so on. So that's the plan as a part of it. Any questions at this point of time?
No, sir.
Hmm. All right. So then let's move on. Move on to the file locking, essentially locking concept. So here onwards, I may not be using too much of the what you call the system for writing programs, compiling them, running them, and all that. I have already shown you enough examples about how to develop programs, how to compile, how to run, and all that. But for this next part, mostly I will be using the textbook straight away, and then try to explain that particular thing straight away. And you can also follow the same material so that it's going to happen two times. Same examples I will be covering, but you need to understand. You need to take a system, try to maybe copy paste or try to type and then see all that kind of thing. Only when you try to type something and all that, some mistakes will happen. That's the a time when you try to actually digest or understand, start thinking. So that's the reason why don't always only copy paste, but instead try to type also, so that some errors you get, and then you start thinking and try to what it is fix those errors there and all that. But now, okay. But now, like what we are interested is the following. See, this is the book actually. I will be following. Beginning Linux Programming, 4th edition, Rocks publication. Beginning Linux Programming, 4th edition, Rocks publication. These files are also shared with you on the Google Drive. You can download and then start preparing along those lines. Sorry. And then this is the actual book. This is the actual book. Beginning Linux Programming, 4th edition, Rocks publication. File locking is available on the 7th chapter. Is available on the 7th chapter. There are so many other things, but we are not interested in these things. File locking is what we are actually interested in. Starting from 264th page, it is actually looking at. So why do you require file locking, right? So that's the context that he is trying to build. File locking is a very important part of multi-user, multitasking operating systems. Programs frequently need to share data, usually through files. And it is very important that those programs have some way of establishing control of a file. Right? Essentially, inter-process communication. Many programs might be running, and you want to share some data by way of a file or whatever. And if more than one program is trying to access the same file, data from the same file, so whereby one program might be trying to make changes, another program might be trying to read the data, that kind of thing, then the data might get corrupted, right? Essentially, you are allowing multiple programs to meddle with the data. So some issues are likely to come up, essentially critical section issues and all that. So for that, how to ensure that only one program is going to get access to that particular file, and after the usage, the other programs can actually get access to that particular. So that kind of stuff. There are different ways, different solutions for that. Start reading, and then you will appreciate what is going on there and all that. Anyhow, so one way of handling these file locking and all is by using something called FCNTL. FCNTL, file control system call. The other one is there is a kind of a library function itself by which you can actually do all such kind of things. So initially by using the FCNTL, so we'll be doing that, and in the process you get to know FCNTL is a very a highly generic system call. In fact, as all of you are aware, the the system calls that we use to work on files are, one is open system call. You are trying to open a file. You are trying to open any kind of a file, whether it is a binary file, text file, or device file. It can be anything. That means it is a highly generic system call, which you can use to open any kind of a file, whether it is a device file, character device, block device, text data, and all. Similarly, read system call, by which you can try to read the data from that particular file that is already opened. This is also highly generic one. Similarly, write system call, by which you can write something onto a file whose file descriptor is specified. No issue. And then close. You try to close the file. So all these things are highly generic kind of thing, which are associated with the data of that particular file and all that. But then there may be certain devices, because you are also trying to open a device also by using open only. But devices may be having different characteristics. For example, you take a keyboard, for example. Keyboard is there on which, you have a caps lock, you have a nums lock, you have a scroll lock and all that. So whenever you click on, you press on the caps lock, you get some LED light. The light indicator will indicate that yes, caps lock is enabled kind of thing. Similarly, nums lock, whenever you press on the nums lock, you get an LED display. So in case you want to get control over those things, it's not like you are reading something or you are writing something, right? You want to do some device specific operations to make caps lock LED on, to switch that particular thing on. How are you going to do that? So these system calls will not help you. Open may help you to open the device, but read and write are not helpful. They are useful only for reading data or writing data. So such kind of device specific operations can be controlled by using a system called FCNTL, file control. There is another system call also called IOCTL, input output control kind of thing. These are the two system calls that help you to perform device specific operations. For example, like you have a CD-ROM drive, CD drive is there. You want to eject your CD-ROM. So already a CD is inserted, you want to eject that particular thing. How are you going to control that? From a program. So reading the data from CD-ROM is different. Yes, you can read the data. Similarly, in case there is a possibility of writing something onto that, that's also possible by using write system call. But you want something different now. You want to eject. You want to eject the CD. So such kind of things are possible by using device specific operations, by using IOCTL and FCNTL kind of thing. So naturally you require proper syntax there, so that should also be flexible enough to control any kind of device. For example, if a tape drive is there, you want to rewind the tape drive, so that you want to go back to the beginning of the tape, right? So like that, any like there are several other things. Let us actually go through these things one by one. Essentially creating like a one way of what it is, uh, one way of exclusive access, one way of getting access, one way of locking a file, or getting exclusive access to a particular file, right? You only, your program only would like to get an exclusive access to a particular resource. So that is possible by opening a file in an exclusive mode. Exclusive mode. So Open itself has got such a facility by which you can open a file in an exclusive manner, meaning that no other program should be allowed to open this particular file. If some other program has already opened that, then this fellow must be made to wait till the other program closes. If no other program is currently using, then this fellow is going to like continue, and then others, in case they want to, they will be stopped from doing that. That kind of stuff. So let us look at these things are also sometimes called as advisory lock. It is not a mandatory lock. Advisory lock means all the programs that are trying to access a common resource, they behave properly. They don't straight away try to go and then start using the resource, right? They all behave they are normally called as cooperating processes. They cooperate with another process in trying to access a common resource. So they don't straight away open or try to access that particular resource. So before using that resource, they verify whether any other program is using that resource or not. And to do that, you have some mechanism which we are going to discuss. And such kind of facilities are called as advisory locks. All the programs are actually verifying before using a resource, right? So that is called as advisory lock. Mandatory locks means system itself will ensure that if one program is already using something, if another program wants to, system itself will prevent. So you cannot actually. So that is a forced kind of thing, right? So we are basically working on advisory locks, this kind of system. Okay, so then now trying to slowly move ahead and all that. So open system call has got these constants called as O underscore create. That means you are instructing the open system call to create the file in an exclusive mode. O create means you are asking it if the file is not there, create also, right? Otherwise, like it doesn't create actually. If you don't use this particular flag, it doesn't create. Similarly, if you use O underscore exl, that means you are also instructing that you want to have an exclusive access. No other program should be allowed. That's what we mean by O exclusive. If you don't use this, then like two programs might try to simultaneously go ahead to like create. But even then, if it is not there, it will create. If it is there, it will continue anyhow. It will allow you. So this enables you to check that the file doesn't already exist and then create it in a single atomic operation. See, this kind of opening a file is done as an atomic operation, right? That meaning that only one fellow is going to execute this particular thing till the end. And the other fellow, the moment you try to start that, because it's already there, he will be made to wait. So simple programs here, locking program, as you can see. So always some header files you require. So these are the header files that you require for writing these things. You are already familiar. UniSTD.h, standard lib because exit is there, stdio and all that because of printf, fcntl, UniSTD because of open system call. Error numbers to handle the error numbers and all that, rno.h you require. So it is a simple lock of this thing. How it's going to work, let us actually try to discuss. It's the main function. So you are not using any command line arguments and all. It is a simple case, no issue. And then int file descriptor. We used to type FD, and here it is file descriptor, complete name. And then int save error number. He is trying to handle the error numbers also. So which we will look into that. So what is the open system call now? Open off. What is the file that you would like to open? Right? So he is trying to open a file that exists in a temp folder, /tmp folder. Any files or any files that you create in /tmp, they will exist only for the current session. The moment you shut down the system, all the files in the /tmp files will be removed. They will all be removed. So if you want to create some temporary files for some purposes or for locking purpose or whatever, you can always create such files there as a part of it. That's a good practice. So /tmp/lck.test. So this is the name of the file. So what are you trying to open with what mode and all that? You are trying to open this in a read-write mode. O_RDWR. That means you want to open this for reading as well as writing mode. And then binary, what it is, OR operator, binary operator, binary OR, right? Or bitwise OR, strictly speaking. So whatever flags that are to be enabled, you bitwise OR all those things. That means you are trying to open the file in read-write mode. And if the file is not there, you want to create it. And also you want to get exclusive access. That's the meaning of all these things. If the file is already there, it doesn't create. It doesn't also complain. But the moment you say O exclusive, if the file is in use by some other program, then this fellow is not going to be given the permission. He will be made to wait. Right? So, or it's going to fail. Or it's going to fail to open. That's what you really mean by. As you can see now, all this, and then this particular thing, because you are also trying to create a file because of this particular thing, create the file with this particular permission. Octal mode you are giving. It's starting with 0, meaning that octal mode. What are the file permissions? So read. Reading means 4, right? Reading is 4, writing is 2, execute permission is 1. File permissions, if you remember. So you are trying to open this file in read mode actually. 4 means only read mode kind of it. So whereas he is not giving write and all that, it doesn't matter. This is not so important. You can as well give 6 also, reading and writing, no problem, right? So this is the mode with which you are trying to open it. In case this fellow is trying to open this and already another program is using it, this fellow will get -1. Open system call will fail. The open system call will fail if it cannot open this file in an exclusive mode. And it returns -1. Otherwise, it returns a meaningful file descriptor. So you are now verifying if file descriptor value equal to -1, because the error number is always going to be the last error number. So while executing a system call, the last system call, whatever is there, that value is available in ER or NO. It is an external variable that is available, that declared in errno.h. In this header file, you will see the actual declaration, and it is an external variable. So always, anytime that a system call is executed, if there is any problem, if there is any error while running that system call, this error is initialized with the error number related to that, right? So you are saving this number into this particular variable, and then you are printing it. Because this printf, while calling this printf in turn uses other system calls. So that's why the ER or NO value initialized by open is going to be overwritten by the other system calls that printf will use. That's why you can't directly use RNO here. That's why you are actually saving this value of that into other variable, and then you are trying to print it. That you have to understand. So open failed with error number so and so. In fact, this is also not required. You can as well say P error of so and so. This is error handling routine. So, and that's all it is. And else open is succeeded. Else open is succeeded. Exit. This is a very small program actually, as you can see, right? By which you are trying to this thing. How do you verify now? You have to run the same program multiple times in parallel, in the background kind of it. Run the same program in the background, run it once again in the foreground. Then two programs are trying to get a lock or trying to open it. So only one will succeed, other will fail, right? So it's a very small program. Slowly you are trying to do this thing. And as you can see, how do you run that? The ./lock1 after compilation. So the moment you say ./lock1, what is that it is doing? It is actually creating a file in the temporary folder, temp lck.txt. So a file is created. So if you again run the same program, file is already there and it fails to create. So that's why you get an error message. As you can see now, ./lock1 open succeeded. Open succeeded is your message, your own message, this message, first time when you are running. When you run the same program second time, you get open failed with error number 17. So the error number what you got while doing second time is error number 17. 17 stands for open is returning, is generating that error number 17. So 17 error actually, what it means, what is the actual message and all that is there meant for file exist. If the file is already existing, you are getting that particular message, right? So, and those error messages and all, they are there in the errno.h, whatever that we have already specified in this header file there as a part of it. So, whenever you want to get exclusive access, this is the mechanism. And remember, like you may not be interested in working on this file. It may be anything to do with some critical section code. A part of the code where you are actually trying to access a resource, not necessarily a file. It can be any other common resource among different programs before using that common resource, try to get exclusive access on this particular file. Once you get access to that file, meaning that no other fellow is using the critical section. So you can enter into the critical section. You can run the code in the critical section. At the end of the usage of the critical section code, you remove the file so that other programs can enter into the critical section. So you are opening the file with creation and you are using the critical section and then you are removing the file so that others can enter. So that's the logic. So the first program is only to have an idea about how to open the file with exclusive access. Now we will actually go into the second program, log2.c. Here you are talking about cooperative log files. How is that? Like multiple programs are going to cooperate and continue. Log2.c. So these are the header files. And what is the log file? You are saying /tmt/lck.test2. This is the file name. Naturally, because it is a string, you are trying to store the into a pointer variable, pointer to character, constant, so that the string message cannot be altered, whatever. So now and then int main as usual, file descriptor. And then now you want to run this program several times by so many programs and then verify like whether critical section can be handled properly or not. So file descriptor int number of tries equal to 10, some variable, so many times. That means that many times you try to enter into the critical section by several programs. So how is that you are going to control that? Let us see. So while tries minus minus, right? So that means you are trying to reduce it. And once because as you know, when tries value becomes 0, 0 means false, so that while loop will exit, while will get out of the loop. So what are you doing here? You are trying to open the file. File descriptor equal to open of log file, read write, create, and exclusive access with these permissions, reading permissions, whatever. If it is failed for some reason, when will it fail? When some other program is already using it. Is already using it, it will fail. So you are simply displaying a message here. What is the message? Log already present. Not only that, some number you are getting. What is the number? You are getting get PID. Get PID is a system call that returns the process ID of the running program. Whatever is the program that is running, its own process ID it's going to display. Meaning that, so it is just simply say like whatever program that failed to get a log, it is saying, so my number is so and so, my process number is so and so, log already present. I cannot get the log. It's already present. I cannot get that particular thing. After that, this is a critical section actually, this sleep 3. Imagine as if there is some code here, right? As if some code is there, right? Or like whatever it is. So strictly speaking, this cannot be the code. This is a waiting kind of thing, you can say. This can be some randomly you are waiting. Sleep for 3 seconds. And after that, else part. Else means what? So this fellow is successful in in opening the file. In case you are successful in opening the file, what do? So I have the log here. So percentage %d, I have the exclusive access get PID. Whichever process that is going to run that. And then now you will have to understand that this sleep 1 is to be considered as a critical section. Sleep 1 is to be considered as a critical section. That code is trying to use a common resource. So use this critical section code. At the end of that, what do? You must allow the other programs also to continue. Because you are now having the log. How do you give the log back? By removing the file. So by removing means first you have to close the file descriptor. So you say close file descriptor. After closing, what do? You have to remove the file. To remove the file, there is a system call called unlink. Unlink is the system call by which you can remove a file. By specifying the name of the file as a string, character pointer, you can remove it. So unlink of log file. So you are opening here with creation, you are also creating that particular thing if it is not there. And then it is successful, only then it will come to this else part. So here you are using that particular log for some time, doing some important critical section activity, and then giving the control back to the other waiting programs, if at all some other programs are waiting, right? So after doing that, this fellow also is waiting. It's like, why is this sleep 2 is there? This sleep 2 is meant, he is assuming that he is doing some other activity. This sleep 3 is to be considered as if what it is, the this program is doing some other activity where there is no common resource requirement. Common resource requirement is not there, so you are doing that kind of one. Similarly, here also common resource is not required. That kind of code you are trying to run. This only common resource. Whoever has got the lock can use this particular code, can run this particular code. That's all. So else this and all that, close, close, close. This is the entire program which you are trying to run 10 times. And if you actually run the same program 2 times, if you run the same program, one in the background, one in the foreground, whatever, then the background program will try 10 times and the foreground program also will try 10 times. Right? So both of them are trying. So only one of them will succeed. But whoever succeeds, he is not retaining the lock forever. After some time, he is returning the lock back, so that at that point of time, maybe the other fellow also will get access to the CPU and all that. He will run the code and then try to again reopen. See, this opening is put into inside the while loop. It is put inside the while loop. So that you are trying, you are failing here probably, but maybe the other fellow is using. So he is actually waiting here enough time. And then the other fellow, after the usage, is actually giving the lock back. He is waiting for 2 seconds, but before that, probably this fellow will get the time there and all that. So that's the idea here. Now, what are you doing? You try to remove the file, if at all it is there by any chance. RM minus F, forced removal. F means force. /tmp /lck dot test2. Because this is the file that you are actually trying to use. Even before running the program for the first time itself, it is there, then always you are not going to get the lock at all. So first remove the lock. And then you are trying to run that. So dot lock2. Anyhow, one thing that he is not specifying to you is compilation command, he is not giving it to you. So he is assuming you already know how to compile and all that. But you know it in fact. So dot lock2, right? You are trying to run that. And then ampersand, meaning that run this in the background. Run this command in the background. And again you are giving. That means run this in the foreground. So one program is running in the background, the other program is running in the foreground. And both programs are trying to get exclusive access to that particular file. So now if you see here, 1284 straight away. 1284 is a process ID. I have exclusive access. So process 1284 is successful in opening the file. Because this fellow is using it, after some time, as you can see, this fellow will release the lock. So the moment he releases, the other program is also running, and that fellow is saying now, as you can see, 1283, because both of them are running parallel. 1283, what is that you are getting? Lock already present. Lock already present. So, and then after some time, 1283 is again saying, I have exclusive access. There is some delay actually in between. The delay is not shown here, but the output is being displayed. So there is an alternatively, like one fellow is getting locked, the other fellow is waiting, and again reverse and all that. So this is how you will actually see. So this is how you can control by using exclusive, by opening the in an exclusive mode. It's a very simple program, right? I hope all of you are following. New things that you are learning is unlink is a system call by which you can remove a file. It's equivalent to RM followed by file, right? And then here you are closing the file descriptor. The unlink cannot be done without closing, because if you don't close it, so file is in use, and if any file is in use, you can't remove those files. Remember that. So closing is very, very important here. So this is a very simple program in this particular manner. I hope all of you are following. Any issue? Internet is okay?
Yes, sir.
Okay, right. Thank you. So, so let's move on to move back to this. So that's about like what it is, working on the files, locking them and so on. But it is okay as long as you want to work in a critical section. But this is not going to give solution for all the problems. What if you actually want to work on, like you want to allow multiple programs to work on some data file actually. You have a very large data file. Here in this case, you are using the file only for assuming, for knowing whether the other program is in the critical section or not. There is no data that is involved in the file. But you are only trying to create a file for exclusive mode. What if you require actually a scenario where there is a large data file on which you want to allow multiple programs to read the data from that file, and also maybe some programs would like to write data onto those files. In that case, how are you going to handle the situation? Right? So this is not the solution right now. That means you want to apply locks onto a portion of a file. The file may be very large. So in order to not mess up with the data and all that, you want to get exclusive access on a portion of a data file, on a part of a file. See, for example, database management systems and all that. You might have a record there. You have written some record. You want to make some changes to the record. Then you find out what is the area within the file from where that record starts and how many bytes is that record actually stands out. So that you want to get a log on that particular record so that no other fellow should be allowed to make changes or read when you are trying to write something onto that. That is exclusive this way. Whereas there is no issue as long as like nobody is writing any data to a file, for example, you can allow any number of users to read the data. If no modifications are happening in any part of the file, allowing multiple users to read the data will not actually will not give you any trouble there because they get the same data, no issue. Only when you want to allow a program to make some changes on the data and allow other programs also parallelly either to make changes or to read the data, then there will be a problem, right? So the same thing you must have studied in database management system and all that. So how are you going to handle such kind of things? What kind of locking mechanism is required in such cases? That is the interest of the this following program, whatever that you are actually talking about, and that is called as locking the regions. Locking a region of a file. a part of a file. Creating log files is fine for controlling exclusive access to resources, such as serial ports or infrequently accessed files, but it is not so good for access to large shared files. Suppose you have a large file that is written by one program, but updated by many different programs simultaneously. This might occur if a program is logging some data that is obtained continuously over a long period and is being processed by several other programs. It is a data logging kind of. Some example he is actually talking about. For that, how are you going to handle that? You can accommodate this kind of situation by locking regions of the file, right? So that a particular section of the file is locked, not the entire file. But other programs may access other parts of the file. This is called file segment, file region, or locking kind of thing, right? So Linux has got, at least he's saying, two ways. One is, just now we said, FCNTL system call. FCNTL system call is what it is going to list. If you think that you are not able to see this, you can even increase the font size, but it doesn't fit the entire thing. It doesn't fit the entire thing. 250 probably we can say. 250 can be enough. They also is not fitting. 240. So I'm only worried whether you are able to see this kind of font or not. That's why I'm just trying to. 230, there should not be any. Almost okay now. I think we are not missing anything, right? So locking the regions. So by using like what it is, FCNTL. The other one is there is a library function called lockf. Lockf is a library function, which we will look into that a little later. But mostly we'll be concentrating on FCNTL system call. And FCNTL system call is available in the header file fcntl.h. What is the signature of this? Signature of this is just like any of the system calls, it returns integer value. Whenever it fails, it returns -1. Otherwise, it returns meaningful number, mostly 0 kind of it. So FCNTL off. That means before using the file, locking and all that, you must have opened the file. So that file descriptor will be used. Whatever return value of the file open system call, that number we will use. FCNTL of a file descriptor. And then a command here. A command which is supplied in the form of an integer value. Right? For different devices, these commands may be different and all that. We will look into that, what those commands are and all that. And then it might require even some more parameters if required. It is a variable parameter kind of system call. So first two are important. Third may be optional. Either you can supply or need not be, depending upon the command here. Some of the commands require extra data. Then for them, you have to supply the third argument also. Some commands may not require any extra data, in which case we can stop there itself. What are they and how to know? We'll study those things. So whenever you want to use FCNTL, we use FCNTL of file descriptor, command, any extra data that is required for that particular command. Right? So let us now look into how locking a region of a file can be performed. So FCNTL operates on open file descriptors and depending upon the command parameter can perform different tasks. The three command options of interest for locking are, these are the commands. See, those are the constants actually, remember that. Just like you give O underscore RDWR or O underscore RD. So these constants are declared in FCNTL dot H. If you know what is the value of this, if by supplying the value also it will work directly. Or by supplying the constants also it will work. Essentially now, FCNTL with file descriptor, there are three different constants having three different functionalities, three different commands. F underscore get LK. LK stands for lock. Get the lock. So that means you want to get the lock information on a region of a file. You want to get the information about, or is it possible to apply a lock on so and so region? Such kind of things are possible by using the command like F underscore get LK. Set LK is possible to apply to get or to get a lock for what you call it is not exclusive lock, it is a shared lock. There is something called shared lock and exclusive lock. This is a shared lock, meaning that you want to read the data from there. So many programs can read the data, no issue, any number of programs, as long as no program is actually trying to write there. So set LK is a shared lock actually, or a read lock, either way you can say. Set LKW is an exclusive lock or a write lock. So how are you going to use them? When you use these commands or whatever, third argument also is required. And the third argument, what it is, its data type is going to be a structure actually. Struct F lock. Struct F file lock. F means file lock. Struct F lock. The structure F lock will contain many fields, and all those fields have to be appropriately filled before actually invoking the FCNTL command. Right? So now you can see the signature of that particular thing is slightly different, as you can see. FCNTL of file descriptor command. The command can be one of these three. One of these three. And then followed by struct flock, and then star followed by whatever. A pointer to that particular structure you have to pass on. You see, FCNTL that is discussed in the previous page is a general one. FCNTL is used against any of the device drivers, not only with locking mechanism. We use the same even to eject a CD drive, even to enable caps lock LED. So for doing any of those things, we can use the same FCNTL. So it is a general thing. Whereas now we are talking about FCNTL with respect to locking regions of the files. There this command can be one of these three values. And then whenever you use one of these three values, then you have to use the third parameter with this particular signature. Struct flock star followed by this. So a pointer to structure flock must be passed on. That you have to understand. Right? So what are the fields within the structure that are available? These are the fields. So short integer, offset t, mostly it is long integer actually, offset t, and then process ID, this thing. All of them are indirectly integer variants, basically. So what information do I require to apply a lock, right? So first of all, what is the type of the lock in which you are actually interested? L underscore type. So what type of lock you want to apply? That you will have to specify. It can be one of those three values. Once again, right? You can specify that. And then, like now you have to select a region of a file, right? How do you select a region of the file? There are different ways. One is, as you can see, L underscore whence. That means you will select a region of the file with respect to the beginning of the file or with respect to the current position of the file or with respect to the end of the file. So by using any of those three different ways, you can specify the region of the file to be locked. So that's why L underscore once can be one of those from the beginning of the file, from the current location, or from the end of the file. It can take any of those three values. Just like your lseek is there, lseek, if you remember, there also you can move the file pointer to the next location with respect to any of those. It's the same actually. It is one among the same. L underscore once. And then you are actually talking about start actually, start of the file. So what is the starting position from where you want to apply the lock? That number you have to specify. And from that particular start point, how many bytes you want to lock? So that how many bytes, that length is indicated by L underscore len. L underscore is nothing but locked, you can say. The actual variable names are type, when, start, len, and PID. Those are the things. So PID means what is the process ID that is currently holding the lock or currently holding that particular region. You don't have to give this like when you are actually calling that, but it's going to be filled whenever you are trying to get to know the lock information on that particular region. That itself is going to fill that. So PID is so and so. So now he is actually talking about the type. L underscore type member takes one of several values. What are those? These are the things. See, the type value can be F underscore RDLCK. That means read lock or trade lock. So you have to initialize with this particular value whenever you want to, right? Get a shared lock. You have to initialize that L underscore type with F underscore RDLCK, all in capital letters. These are the constant values that are already declared in FCNTL.h. Similarly, if you want to unlock, already a lock is there, you want to unlock that so that others can use it. Then you say F underscore unlck, right? This is how you can remove the lock. And then in case you want to get an exclusive access to that particular region, you say F underscore WRLCK. Exclusive lock or write lock. Simple words, right? So no issue so far. I think all of you are following what's going on. So L underscore once, L underscore start, and L underscore len members define a region, contiguous set of bytes in a file. Now the L underscore once, what kind of value can be assigned to L underscore once? The values are one of these three, from the beginning, from the current location, and from the end. And what are the corresponding values? They are available in unistd.h. And the constant values are seek underscore set, seek underscore cur, seek underscore get. Seek underscore set means from the beginning, seek underscore cur means from the current location, seek underscore end means from the end of this one. Right? So whatever is the start that you specify is with respect to these three parameters. Right? So I think you are slowly following everything. And then PID is used for reporting the process holding a log, and especially useful when you use F underscore get LK as a part of it. Now slowly a kind of a small program can be written to understand those things. So F underscore get LK, right? So this is the actual command as a part of FCNTL. And these are the parameters. Already you are familiar with this particular thing. What will happen? The first command is it gets locking information about the file that file descriptor has opened. It doesn't attempt to lock the file, remember that. It's only getting the locking information. You are not locking it. You are only getting the information about the lock. Or is it possible to apply so and so lock? So that kind of thing. The calling process passes information about the type of lock what you want, right? And fget lk command returns any information that would prevent the lock from occurring, right? So it might wish to create and all that. The values used in the f-log structure are all these things. So they are the same values, what we have already discussed about. A process may use fgetlk call to determine the current state of logs on a region of the file. Right? And then it's talking about all that. The fcntl call, look at it. fcntl call returns a value other than -1 if it is successful. That means if it is possible for you to get a log of that particular nature, you get other than -1. -1, if you get, provided it's not possible for you to get that kind of a log. Then you will also get other details. What is the process that is currently holding? All those details will be filled. So if the f underscore get lk call is unable to obtain the information, it returns -1. Minus. If the get lk call is successful, it returns a value other than -1. And all the other details are there as a part of it. It is a very simple system call. Similarly, set lk, in order to apply what it is, in order to apply a read lock, you are going to use this particular thing. So L type is going to be one of these things. F underscore RDLCK, WRLCK, unLCK, one of the following, whatever. And PID is unused. So whenever you are calling set LK, these fields are to be initialized. Remember that. Whereas whenever you are using get LK, these fields are to be initialized before calling. Before calling, these fields are to be initialized. Remember that. And other what area of the thing is to be applied, all that also you have to actually specify that. This command attempts to log or unlog part of the file. The values used in the flog structure and different from those used by getlk are as follows, as it is. So here f underscore rdlck, wrlck, unlck to unlock. Whereas the type here, L underscore type, either f underscore rdlck or f underscore wrlck can be applied here. RDLCK, WRLCK. Whereas here, if you see RDLCK, WRLCK. Unlock also is possible here. Similarly, set LKW is meant for getting the exclusive access. So now you can actually start writing a small code, reading and writing with locking kind of it. So 230 is not yet. Okay. So you can look at this particular program. Probably it's now 10 o'clock, yes. So what we can do is, I just will stop at this particular place. Just go through this book, read it, and next class when you come, we will try to complete this locking mechanism, and also signals is there. Signals is another small topic. Those two we'll try to complete in the next Thursday class. But try to actually start reading these things. So this is the 7th chapter. Signals chapter also is there. A part of it you can read it and then come. We'll complete the session in the next class. I think you are slowly following in line, right? So we'll close the session at this point of time. So what it is, recording need to be stopped.